Okay, my name is Nick Ryder, and I'm here to present on real stability testing. This is joint work with Prasad Raghavendra and Nikhil Srivastava, who are both in attendance. So first, I'm going to start off by introducing real stable polynomials and giving a definition of them and giving you some examples of them and mentioning some work they're used in. Then I will talk about our main reduction in our paper, which uses convexity results about hyperbolic polynomials. I'll talk about how we then solve our reduced problem, and I'll wrap it up with a little comment on non-negativity testing, which we'll need. Okay, so real-rooted polynomials are classically studied objects that have lots of nice properties. So if you look at generating polynomials for combinatorial objects and you know that the generating polynomial is real-rooted, you get information about the coefficients, which tells you stuff about the number of combinatorial objects you're counting. So in that instance, you get ultra-log concavity of the coefficients. Another thing you can take advantage of with real-rooted polynomials is that the roots are real, and so you can abuse the total ordering of the real numbers to get properties about interlacing. So interlacing arguments were the main tools used in recent papers to prove Kaz and Singer and the existence of Ramanujan graphs. So real stable polynomials are the natural a natural multivariate extension of real rootedness. So when you're looking for a multivariate extension of real rootedness, you're going to want some information about the zeros, but it's not obvious at first glance what to do. So the definition of a real stable polynomial is we have a multivariate polynomial with n inputs, and we're exactly going to look at the polynomials where when we look at inputs that all lie in the upper half plane, the polynomial doesn't vanish. So if your inputs all have imaginary part that's positive, your polynomial doesn't vanish. So the nice thing about real stable polynomials is they have a lot of closure properties. One of the closure properties is that if you specify all your variables to be the same, so you can diagonalize your polynomial, you'll still get a real stable polynomial. So it's really important to understand what are the univariate real stable polynomials. So if you have a univariate polynomial with real coefficients, since its roots come in conjugate pairs, if it doesn't vanish on the upper half plane, it also doesn't vanish on the lower half plane. And so the only univariate real stable polynomials are real rooted ones. So this is the classical method you'll see to apply real stability. You'll use machinery to talk about multivariate extensions of polynomials, and then you'll diagonalize those polynomials to then prove classical results that certain univariate polynomials are real rooted. And so this mainly showed up, like I said, in the recent work on, or not mainly, but one of the cases where it showed up is in the recent work on the existence of Ramanujan graphs. In that case, they used the matching polynomial. So if you look at the multivariate matching polynomial, which counts matchings of an undirected graph, that's a real stable polynomial. Another example is determinantal polynomials. So if you're given a bunch of positive semi-definite matrices and a Hermitian matrix, you can look at the multivariate polynomial formed in this way, and it'll always be real stable. So you should think real stable polynomials as behaving a lot like polynomials formed by the determinant. And the final example I want to give is symbols of real stable preserving linear operators. So if you're given a real stable, or if you're given a linear operator, a natural question is when does it preserve real stability? It turns out for every linear operator you can associate a polynomial, which I'll talk about a little bit more in a second, called the symbol. And the given linear operator preserves real stability if and only if its symbol itself is real stable. Okay. So the second example I gave was these determinantal polynomials, and there's this really nice theorem of Helton and Vinnikov that says that every bivariate real stable polynomial is in fact of the form of one of these determinantal polynomials. So there exist real symmetric matrices A and B and a Hermitian matrix C, positive semi-definite matrices A and B and a Hermitian matrix C, such that your polynomial is this. So for bivariate polynomials, we actually know a lot about the structure of them. We can write down explicit linear algebraic representations of them. This is not true for more than two variables. So this is one of the nice things that we find with bivariate real stable polynomials. Another application of bivariate real stable polynomials is if you're given a linear operator from univariate polynomials fixed degree to all univariate polynomials, one natural question is when does it preserve real rootedness? So an example of such a linear operator would be differentiation, or polynomials, real rooted polynomials in differentiation. And a nice theorem, a recent theorem of Brescia and Brendan, shows that there's a bivariate polynomial you can associate with any linear operator called the symbol of t. And the t preserves real rootedness if and only if its symbol is real stable. So if we can test bivariate real stability quickly, then we can answer this question. So this is the problem we're going to try to solve. Given a polynomial, a bivariate polynomial in x and y of total degree n, does there exist a strongly polynomial time algorithm to determine if it is real stable? And our main result is that there exists an algorithm to determine if it is real stable, which takes order n to the fifth arithmetic operations. So what was known previously, there weren't any explicit complexity results established for this, but there were some papers that mentioned some weakly polynomial time algorithms. One of those methods would be quantifier elimination. Since we're looking at fixed degree polynomials, we're looking at bivariate polynomials, quantifier elimination will lead to a weakly polynomial time algorithm. Another thing is using a semi-definite program via some machinery in control theory called discrete time spectral factorization. So this was established in a paper of Henrien. OK, so how are we going to tackle this problem? So there turns out to be an equivalent definition of real stability that lends itself much better to algorithmic approaches. And it's an easy exercise to see that the two definitions are equivalent. So I'm also going to define hyperbolic polynomials in a second. And the main definition for both of these will be looking at linear restrictions. So we'll put into the inputs linear polynomials in a single variable t, and we'll want properties of those linear restrictions. So for real stability here, we want to look at linear restrictions that have positive slope. And we want the requirement to be that when we look at any such linear restriction, it's real rooted. So if we think about linear restrictions in the plane that have positive slope, this is a two-parameter family of lines. And so when we look at this problem, it's not so hard to parameterize this as we're looking at polynomials who have coefficients in two variables. We have a polynomial in t. Its coefficients are polynomials in two variables. And we want to see for all linear restrictions, all assignments of those two variables, we get a real rooted polynomial in t. And the main problem we ran into is that we could not figure out how to establish a strongly polynomial time algorithm for two-parameter families, this two-parameter question. And so what we do is we use convexity results about hyperbolic polynomials to reduce to a one-parameter family, which naturally which we can use classical machinery to extend our classical machinery that tackles how to determine if a univariate polynomial is real rooted to, we can extend that and solve this problem. So let's introduce hyperbolic polynomials. So just like real stable polynomials can be defined by real rootedness of certain linear restrictions, so can hyperbolic polynomials. So a hyperbolic polynomial is a homogeneous polynomial, and we say it's hyperbolic with respect to a certain direction e if all linear restrictions with that direction are real rooted. So one natural object that people associate with hyperbolic polynomials is the hyperbolicity cone. So if you have a hyperbolic polynomial p and you have a direction with respect to hyperbolic to e, then you look at the hyperbolicity cone, which is the connected component of the non-vanishing set of the polynomial that contains that direction. And the reason that people look at this is because of this theorem. So given any hyperbolicity cone, you're guaranteed that it's an open convex cone, and you're guaranteed that every point in that cone is a direction for which p is hyperbolic with respect to. So these are going to be the two main points we use to reduce a problem from a two-parameter family to a one-parameter family. I should note an example of a hyperbolicity cone is the cone of positive semi-definite matrices. OK. So how do we connect hyperbolicity and real stability? Yet again, our goal is to determine if a given bivariate polynomial is real stable. And so an easy exercise is not so surprising, since hyperbolicity is defined in terms of real rootedness of linear restrictions, and real stability is as well, that you can just kind of use the definition to show that if you homogenize a bivariate polynomial, the original polynomial is going to be real stable if and only if its homogenization is hyperbolic with respect to a set of directions. And that set is going to be this upper quadrant. So remember that the hyperbolicity cone is an open convex cone. And so if we can show that our function does not vanish on this line segment, then by the fact that it's a cone, we'll be guaranteed that our polynomial does not vanish on this whole upper quadrant. Furthermore, p is hyperbolic with respect to every point in the cone. So it suffices to just show it's hyperbolic with respect to one point in the cone. So if we can show our polynomial is hyperbolic with respect to one direction in this quadrant, and we can show it doesn't vanish here, we'll be guaranteed that it's hyperbolic with respect to everything in this quadrant, and therefore real stable. OK, so in total, this is that reduction. And I write out in coordinates what each thing's happening. So we want it to be strictly positive on this line. So that equates to just this univariate polynomial being strictly positive. We also want pH to be hyperbolic, and we can reduce that to showing that for every real gamma, this polynomial here is real rooted. So the first problem is a classical problem. Determining if a univariate polynomial doesn't vanish on an interval has a lot of machinery associated to it. So for example, Sturm sequences. It's not so important to know the details here, but there's these things called Sturm sequences. You use a variant of Euclidean division to get a sequence of n polynomials of degree at most n. It takes O of n squared time to compute this sequence. And once you have the sequence, you can query it in linear time to determine the number of real roots the polynomial has on any given interval. So this solves the first part of our reduction. And the second part of our reduction then is the main problem we have to tackle. So this is exactly what I mean by a one-parameter family of polynomials. I have a family of polynomials which is parameterized by gamma. So for each gamma, we get a polynomial in T, and the coefficients of T are polynomials themselves in gamma. And we want to determine if, for all evaluations of gamma, the corresponding polynomial is real rooted. So how do we do this? We use classical machinery that's used to determine if a univariate polynomial is real rooted. So one way to determine if a univariate polynomial is real rooted is to use the moment matrix. So we look at the moment matrix, which is a Hankel matrix formed by the moments of the roots of the polynomial. And the theorem is that a univariate polynomial P is real rooted if and only if the associated matrix is positive semi-definite. So how do we check positive semi-definiteness? Well, there's a lot of ways to do this. But because we're going to want to generalize this to one-parameter families, we're going to want to view PSD as a semi-algebraic variety. So namely, we're going to want to view it as cut out by a bunch of polynomial inequalities. Oops. So to see this, just note that a symmetric matrix is PSD if and only if its characteristic polynomial has non-negative roots. And a polynomial has non-negative roots if and only if its coefficients alternate in sign. And so therefore, we can look at the coefficients of the characteristic polynomial. We can check some sign condition on them, and that'll tell us whether or not our matrix is PSD. So now how do we extend this? Well, our one-parameter family is always real rooted if the associated moment matrix is PSD. But what does our moment matrix look like now? Now our moment matrix has entries which are polynomial functions in gamma, right? The moment matrix, by Newton's identities, has entries which are dependent on the coefficients of our polynomial, but now our coefficient of our polynomials are polynomials themselves in gamma. And so our moment matrix is going to be polynomial functions of gamma. Therefore, the characteristic polynomial has coefficients which are polynomials in gamma. And so we want to recover these polynomials in gamma and guarantee that they're all non-negative. To recover them, we just use interpolation. And so this method takes O of n to the 7th arithmetic operations to output n polynomials of degree most n squared, which we need to check are non-negative. I'll briefly mention a faster way we do this in the paper, but not talk too much about it. So there's a classical bit of machinery called subresultants, which is how you quickly compute Sturm sequences and do a lot of things in real algebraic geometry when you're working with univariate polynomials. And it turns out that there's a way to talk about non-negativity of the Sturm sequences relating to real rootedness of the polynomial. And yet again, these Sturm sequences will be polynomials in gamma. And the nice thing is you can calculate subresultants a lot faster than you can calculate the characteristic polynomial. And so the time to calculate the subresultant sequence, instead of being O n to the 7th, ends up being O n to the 4th. And this is nice because it'll move the bottleneck of our algorithmic time to the last step. So what you can think we're doing here is, so to review, we had a polynomial, a bivariate polynomial. We wanted to determine if it was real stable. To do this, we did a reduction to a one-parameter family. And that one-parameter family, now the note is that if you want to determine if you want to look at the set of all one-parameter families of polynomials where all the restrictions are real rooted, that's a semi-algebraic set. And so what we've really done is just figured out a bunch of two different sets of polynomial inequalities that define that semi-algebraic set. And so now we've reduced to showing a set of n polynomials in degree most n squared are non-negative. And so the classical method to determine non-negativity is semi-definite programming. But to keep this strongly polynomial, we just show that there's this algorithm. We assume it's just a folklore algorithm that runs in O of n squared time. So if you're given a univariate polynomial of degree n in O of n squared time, you can determine if it's non-negative by first getting rid of all the square part to reduce to the square free part and using Sturm sequences. Since we have n polynomials of degree n squared, the total time of this step is O of n to the 5th. So this is where the O of the n to the 5th comes because the Sturm sequence calculation was O of n to the 4th. So as a summary, bivariate real stable polynomials are nice objects to study. They show up a lot. And one of the key places they show up is that they are equivalent to checking if a given linear transformation preserves real rootedness. The problem a priori is a 2-parameter problem, which doesn't lend itself to strongly polynomial time algorithm. But using convexity of results of hyperbolicity, we can reduce it to 1-parameter problem. And we can extend classical machinery like moment matrices or subresultants to then solve this 1-parameter problem. Outlook. So more than 2 variables, the biggest thing seems to be non-negativity of bivariate polynomials. So we're not aware of any algorithm to in strongly polynomial time determine if a given bivariate polynomial is non-negative, although I'd love to hear if anyone knows more about that. Another way forward is to determine if there's a strongly polynomial time algorithm. So basically the last part of our algorithm says we want to determine if a given homogeneous polynomial in 3 variables is hyperbolic with respect to a given direction. Another question is, OK, you give me homogeneous polynomial in 3 variables. Does there exist any direction with respect to its hyperbolic to? And we're not sure if there's a polynomial time algorithm to do that. And the last thing is we didn't really consider complex coefficient stability. There is a notion of this. It's also pretty important. And a lot of the tools we used were real algebraic tools, such as Sturm sequences and subresultants. And so we didn't really explore this route, but there very well could be something here. Thanks.
Questions, maybe?
Yeah.
If you look at all of any of these algorithms are doable in something smaller than P, like NC, a lot of these type algorithms, I think have been shown in that.
I don't know what result to do, but
Yeah,
you're
we-
right. I haven't really thought about it.
How about finding the 3 matrices?
Oh, yeah. So we briefly looked into that problem. And I guess, Nikhil, you concluded that it's...
Well, so the status of that is that there's a paper which does it, so it won't be strongly polynomial, surely, but you can get complex matrices, but it's not known how to get real PST matrices.
There's multiple methods for getting complex Hermitian matrices. Some are algebraic geometric, some are use spectral time factorization, stuff like this.
The 2 positive definite and the Hermitian matrix that...
Yeah.
Yeah, so you can get them if you allow complex numbers.
Oh, I
There
see.
are algorithms.
So I'm sorry, I missed one point maybe. Is polynomial time algorithm known for this? Because we're talking about strongly polynomial time algorithm.
Yeah, so there probably are some weakly polynomial time algorithms.
What do you mean by weakly polynomial time?
So that depend on the bit complexity of the inputs.
Okay, that's standard.
Like quantifier elimination or...
Thanks.
Yeah, we'll go